All right. So 3.4. is really going to be based directly off of 3.3 with the Taylor and Maclaurin polynomials. This section is labeled Taylor and Maclaurin series, so it's basically going to be based off of that section. So anything that you had to memorize for that section should also be memorized for this section. And there will also be some problems where we'll see in some of the examples where you will have to remember some of the tests from 3.2, like your note cards. So yes, it's just going to keep building on from each section. Well, you're going to have some trouble. Alright, so if we start out, we're going to start out with Taylor and Maclaurin series today. So if x is a variable, then an infinite series of the form, right here, you can read this. This is called a power series. I'm not reading it all out. That is called a power series centered at x equals 0. Remember, when anything's centered at 0, we think of what?
Maclaurin.
Yes, Maclaurin. Okay. So what we're going to say in this section, though, is that we have something that's equal to a function. Last section we said it was approximately something because we were stopping at, we talked about 5th degree, 9th degree, something. We were stopping at some location there, and it was approximate to something. But we're going to a to the n, x to the n, so we're going all the way out, and then it has dot, 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 so we're continuing on infinite series here. So it's going to be equal to some f of x function. A power series, this is a series with x in it. So we see there's an x right here. It's a series that has x in it. That's what a power series is. We have this example down here too, the same as up above, but we have x minus c. So this one is centered at x equals c. So again, like the Taylor and Maclaurin polynomials when we talked about those, the x minus c, your c will be where your center is if it's not at 0. And again, this will be equal to some function. We'll just say g of x. It won't be approximate, it will be equal to. So before we get into all the details down at the bottom, I'm going to just draw a little picture to kind of demonstrate what we're trying to get at here. So I'm just going to draw right here. So if we start out with the function like ln of x, goes something like that. We have the asymptote here because it can't go over x equals 0. So this would be y equals ln of x. And like in the previous section, we were trying to find those approximate different values. But what we're going to say here is we're going to have some series that will approximate, in this case, ln of x. Now we're going to have three different options of what it could represent. It may represent it only at one point. It could represent it on all real values, the entire distance of the function. Or it may be in some convergence interval that we'll talk about, within a certain interval that it could be exactly the same. So if we have ln of x, we know at 1, it's going to start right there. And we could have some quadratic function that would exactly map it, but then it's going to go like this. If we had some quadratic that we could find that is going to be the same until some point, but a quadratic, of course, is going to come the other direction. So it's not going to be exactly the same. A quadratic, yes, does have a domain of all reals. But as we can see from these two functions, they're not going to be exactly the same on all real numbers, because we can see the quadratic comes back down in the negative direction. But what we might be able to do is find an interval on where those values are exactly the same for those functions. So in this case, it may be something like we can find +1 in this direction, -1 in this direction, and within that interval, those functions would be the same. So in that case, it may be from some interval 0 to 2. And as an example, ln is never going to 0, so that would have a parenthesis. But you do have the option in these problems, and you'll have to test your endpoints to determine whether it's included or not. So we could find some polynomial where it may go to that 2 as an x value, and they would still be the same. And after that, it would start to differ. So we do have the option for parentheses or brackets, and we will see that more in depth with the first few examples. But this is just kind of visual of one way that a problem could work out. So we may have some examples where we find functions that graph exactly the same for the entire function. We'll talk about that more, but if we think about back to the last section, like sine of x, as you added on more terms to your polynomial, it graphed further and further on the function. So if you go out to infinite terms, you could imagine if you write out infinite terms, it's going to map exactly onto the sine of x function. So the equal sign above means that the left side equals the right side for all the values in the domain. This means the above is an identity. But for what values of x does the identity hold? We have to find them. For all such x values, we say the series converges. For the values of x for which the identity is not true, we say the series diverges. So in terms of this problem that I kind of just made up here, we would say it converges from 0 to 2, but outside of that range, anything would diverge. All right, so furthermore, for a power series centered at x equals c, exactly one of the following is true. Yes, sir?
So that graph you drew, so that's just an example problem. You're not saying that the series, these power series, are going to follow ln of x.
Yeah, we don't have, in this example, this function isn't following ln of x for all the values. We see this would be some quadratic, but what we're saying is we can represent on this interval, it would be exactly the same. It's not just an estimate. And then we're going to say, well, we could find some, maybe we're not representing ln of x, but when we talked about sine of x, we can find some polynomial infinitely that would map exactly on those values. So sine of x would be an example of that.
So it doesn't have to be ln of x?
No, that's just an example that, just to get a visual of something that we're dealing with, that's what I had put up there. And we're going to go through some examples on the back where we don't have anything with ln of x. Okay? We'll see multiple examples. So number 1, the series converges only at x equals c. So we're saying right here would be the center of your ln of x example that I just gave, and this other function, this quadratic. So we're saying at that point, it converges at that point. We know that they're starting at the same spot, so they have to be exactly the same. Number 2, the series converges for all x's. So again, that's like we talked, like sine of x, e to the x, cosine x. Those ones you have memorized from last section, right? Yeah. All memorized. So those ones infinitely written out to the nth power, and again, dot, 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 continues on. It would map exactly on sine of x, cosine of x, and e to the x for infinite terms. There exists an r greater than 0 such that the series converges for the absolute value of x minus c. This would read within r units. That's what this would mean, within r units. And diverges for x minus c out of the x, or out of r units. So in other words, and it's written down below, going to have a bracket or a parenthesis, because remember we can have either one, c minus r, c plus r. So we're just saying we can find what this r is and add and subtract it to c, and we'll find that interval. And again, an example of this is kind of like what I was explaining with up above. That radius of convergence, for this example I said was +1, just as an example. We didn't physically find it mathematically, but just as a visual I said it was 1. So if you add 1, you get to the 2. If you subtract 1, you get to the 0. So that's what this is saying down here. R is called the radius of convergence. So again, that's what I described with the +1 and -1. Again, right here, so radius of convergence. In part 1, so these are referring back up to these. Yep, right here. So 1 is referring to this one, 2 is referring to that 2. So it says in part 1, the radius is 0. So if you're centered at 0, and that's the only, that it only converges at that center, you know your radius is 0. So if you go any bit to the left or any bit to the right, you know that it's not exactly the same. It only converges there. So the radius would be 0. In part 2, if you have that example, so you're saying your series converges for all x values, again, sine of x, if you have that infinite polynomial, you're saying your radius is infinity. You can go any distance to the positive, any distance to the negative, and you're going to be exactly on as long as you have that infinite polynomial. Again, last section we were stopping at like 9th degree, 5th degree. So we're not stopping, we're having the infinite polynomial. In part 3, again, this kind of refers up to that example that I showed at the beginning. We have some interval c minus r and c plus r. This is the interval of convergence, or the domain of the power series. So again, in that example I showed up there, within that interval we could be exactly the same. But outside of that interval, we're not the same. Note, to determine if the endpoints are included or not, we must test each endpoint independently. We typically use the ratio test to determine the radius of convergence. Does anybody remember the setup of the ratio test before I start writing some down? We have a limit as n goes to infinity of what? What's the general setup?
The original function over the
Yeah, and
It's the n plus 1 function over and over to.
yeah, it's the n plus 1 over the original absolute value.
Oh, yeah.
If it is less than 1, what's your conclusion? Converge. Greater than 1. And equal to 1. Inconclusive. You're getting there. So less than 1's converge, greater than 1's diverge, equal to 1 inconclusive. So this is the one that they're telling you is used most often with these types of problems. It's not saying that we're not going to use other ones, but this one is most often used. We ready to go to the back?
So which test is the one where it's the original over? Oh, that's limit comparison.
All right, on to the back. So it says, based on the fact that a 4th degree Maclaurin polynomial for e of x is listed right here. So this would be 4th degree. Again, this is not infinite. That would be considered, and I'll write it here, this is when we do the approximation of e to the x. That one's known as an approximation. It's an approximation because there's finite terms. It's with the infinite amount of terms it becomes an equals. Says find the nth term, then find the radius and interval of convergence for the representative power series. Okay, so when we talk about the nth term, how could we represent the nth term from e to the x of the Maclaurin series? So kind of think of the pattern of the Maclaurin series. What does it mean when we talk about just the nth term? How would you write the nth term of the Maclaurin series of e to the x? Just a one single term. Fraction. What's on top, what's on bottom? You can use some of the information given in the problem to help you. They give you a 4th degree. I just want to know what the nth term would be. Well, that would be listing out the whole thing. I just want to know one of the terms. I want to know specifically just the nth term. I don't need all the terms leading up to it or anything after.
X to the n plus 1 over... Oh, yeah, I guess you could just be n.
Yep.
So x to the n over n.
Factorial. Yeah, that would be the nth term. We're just taking that from the pattern of e to the x. If I take the nth term, it's just going to be x to the n over n factorial. Okay, so now it says that we typically use the ratio test. Yes, ratio test. So we want to find the radius and the interval of convergence. So that's what we're trying to find. We are going to use the ratio test to help with that. So as we said, we need the limit as n goes to infinity. It is absolute values. What would be our setup? Again, we have it the an plus 1 divided by an, but remember it's easier to just do what?
Just automatically just
Multiply by the reciprocal. Yep. So we have xn plus 1 n factorial over n plus 1 factorial x to the n. Now we need to go ahead like we did with these problems before and simplify anything that we can. Can I rewrite anything on the top or the bottom? So if you want to check what I got, I have x to the n on the top times x times n factorial. That's just simplified on the top. On the bottom I have n plus 1 times n factorial times x to the n. Again, simplified the bottom. Now I can cancel out terms. Any questions on how we got to that part? Okay, canceling out terms, I'm left with x over n plus 1. If I take the limit is equal to what? This one, at first might be a little confused because we have what? We have x and n. Which one are we taking towards infinity? N. So we're actually, in this case, treating x as like a constant. Pick a number for it, plug in towards infinity for n, and you get what as your value for your limit? 0, that is less than 1. And if you think about it, if you plug in any x value, will it always go to 0? If you plug in any constant value for x? Yes. Okay, so it is less than 1. That's always true for any x. So now what do you think we can say about our radius or our interval because of what we found? Okay, we know it converges where? It would converge everywhere. We found that it is less than 1, so we know the entire infinite series that we're dealing with. By the ratio test, it converges everywhere. So our radius, I'm just going to write equals to. Radius is equal to infinity, because no matter where you go, it's going to be the same. So the interval is equal to negative infinity, comma, infinity. So there's no restrictions on this one. If you have the infinite polynomial, if you don't have the finite terms, but the infinite one, on all values, negative infinity to infinity, it will converge. Now for some of these examples that we're going to talk about, like we talked about this e to the x here, but we're going to have some examples moving forward, especially I think the next example, in example 2. We're going to be able to use this test to determine and find some interval where this converges for some type of other function or polynomial, but we're not necessarily going to know what that other function is that it converges on. We know that there's something else out there that exists, that it is exactly the same, but we're not going to know, like in this problem, it was e to the x. In the last section, we knew we were dealing with sine of x and cosine of x. With these problems, we're going to be able to determine if it does converge and what that interval is, but we don't actually know what it's going to be compared to. Okay, so we don't necessarily know what that original function is that it is the same as. And we'll see that more in example 2. With this example 1, we know that we were comparing to e to the x.
So how do we know the radius was infinity just because it converged?
The way that this problem worked out, we know that it was the limit was 0, so it was less than 1. So we know that this one converges. By the ratio test, it converged. So there's no stipulations with that. It converges everywhere. By that test, you know that it's going to converge everywhere. So what we're saying is this polynomial, if it was written out to infinite amount of terms, would converge on each point, so it's exactly the same as e to the x if you write it out to infinite amount of terms. Again, if you limit it like in the last section, finite amount of terms, like this is the 4th degree, it's approximate, it's close, but if you write out infinite amount of terms, we're saying on that interval, negative infinity to infinity, it's going to be exactly the same. I think example 2, part A, will make it a little more clear on how to use this. Okay. All right, let's go ahead and start that one then. So, find the radius of convergence. Well, actually, before we go there, I think I mentioned this. Let's read what the note there. Often we will be dealing with power series representing unknown functions. So that's kind of what I had mentioned before we started this. While we may not recognize the function the series actually represents, we can still determine the values of x for which it does represent the unknown function. So that's what I was talking about before we start these ones. We don't know what we're comparing to, but whatever it is compared to, we know it represents something. We just don't know what that something is that it's representing. So find the radius of convergence in the interval of convergence. Be sure to test the endpoints independently. So we're going to find some interval, and again, we're going to have to test each of those endpoints. So, as we start, do we know what the center of convergence is? The center of this. What does C equal to? 5. So what we're saying, whatever this is compared to, we know at 5 that it converges. So we know for sure it converges at 5. Converges at 5. We know that for sure. But we're going to go ahead and try the ratio test. So limit n goes to infinity. We have x minus 5 to the n plus 1 over n plus 1 times 2 to the n plus 1. Again, that's just plugging n plus 1 in for all your n terms there. And it's absolute value, so the alternator doesn't really matter. Multiplied by the reciprocal of the original, n to the 2n. So again, the n plus 1 multiplied by the reciprocal of the original. So you don't necessarily have to write out all these steps if you can do it in your head. So is there anything that's going to cancel? If you want to write it out, you can. You don't have to. Is there anything that's going to cancel? What are we left with on the top? What are we left with on the bottom? Anybody find the reduced top portion numerator yet? X minus 5 what? Sorry?
X minus 5 times n.
Yes. Okay, that's the top. What's the bottom?
2 times n plus 1.
Yep. Okay, so that's our top and our bottom of our reduced one. We canceled out our terms. Let's see. What else can we do? So if we think about n going towards infinity now, how does that really help us here? Or what does that tell us? If n was going towards infinity right now. Well, we'd have infinity over infinity.
But doesn't the times 2 plus 1?
Well, infinity plus 1 really,
Still,
yeah, it's with infinity and infinity plus 1 that really is not enough to vary.
the 2 things is just x over 5.
But then we have something here. This is some constant term, so this is also infinity times some number. So really, we can't really tell at this point. What we can do is we could make this as x minus 5 over 2, getting rid of our n terms, almost kind of like, think about L'Hopital's rule because infinity over infinity. So we have x minus 5 over 2. And what do we want that to be less than? What would we like it to be less than? Thinking about ratio test. 1. Because we know if it's less than 1, it will converge. Well, we have this 2 on the bottom. Let's go ahead and get rid of that. X minus 5 less than 2. Let me move that up some. So again, what we're working towards right now is trying to find what that interval of convergence is. And we'll find that in the radius of convergence. So from here, what we can tell with this form right now, we can find our radius of convergence. So we know we can pick some x values. Are there some x values you can pick that would be less than 2? Aren't there some x values that would make sense there? Yeah, so what we're saying here, we know the center is at 5. We have that from the original. So we're saying from 5, we know it has to be less than this 2. Well, this 2 is what's known as our radius. So visually, if you think of, you don't have to draw this if you don't want to, but you can. If we have 5, that's our center. We're saying the radius is 2, so we could go plus 2. We could go minus 2. We're thinking about the radius around 5. So we could go plus or minus 2 on either direction. If I plug in 7 minus 5, we have that less than 2, so that's right on the interval. And 3 minus 5, less than 2. So this creates our interval. We know that we have 3 and 7 because we're plus or minus 2 there. So we know our interval is 3, 7, but we don't know yet if it's parentheses, brackets. That's what we have to determine. So we know we have 3. We can write it like this because we're undecided yet, parentheses and brackets. So that's, we haven't tested yet. We know that we either need parentheses or brackets, but we need to test it. So are we okay up to this point determining, yes, we know if it converges it has to be less than 1, but we made it equal to our center here, so we know the radius has to be 2. Are we okay with the steps we've gone through so far?
How do you know to get rid of all the ends?
So from here to here, we know at this point that we have some like indeterminate. We can't do anything with it. We can't decide. So you have to just try to go through any processes that you know. In this case, we know if we have just the 2, or x minus 5 over 2, we can do something with that. We just have the x there. And we know that we want it to converge or be less than 1. So kind of thinking, like I said before, like L'Hopital's rule, if you take derivative of top and bottom, you can find your limits.
So you're treating x minus 5 as a constant?
Yes. Just like up, where was it? This example 1, we had to treat x as a constant up here. Because we're not truly plugging anything in for x at this time. We're treating is it some value, but we're saying that n's going towards infinity while this x is some value. Okay? Alright, so now we found the interval. What you have to do is test each endpoint to determine whether we have parentheses or brackets. So we're going to, and I'll erase for the next example, so I'm going to write it over here. We're going to test x equals 3 first. So whenever you're testing these endpoints, this is really where it could get into you, depending on the problem in the setup, could be using any of the tests from 3.2. Those ones that you had for the quiz. So that's when any of these are fair game, or when you get into testing these endpoints. What we're going to do is we're going to test 3 for x, but we're testing that in the original. So we have -1, n plus 1, times, well, if we plug in 3, 3 minus 5 is -2, so -2 to the n, over n times 2 to the n. Okay, so this is the original testing the endpoint of 3, though, for x. So now we need to decide whether it diverges or converges. That will tell us whether it's parenthesis or bracket. So we need to start reducing and see what kind of test we might be able to use on this. So is there anything we could possibly cancel? Or something that you think could be canceled, but you're not exactly sure how to cancel it yet? Okay, so we have 2 to the n here, but we have -2 to the n here. So they're similar. Is there a way we could make them look the same? There.
Just pull out a -1 to the n.
Yeah, we could change this to -1 to the n plus 1, pull out a -1 to the n, and multiply it by 2 to the n. -1 to the n times 2 to the n would just be -2 to the n. Now the 2 to the n's cancel. We have the same bases here, -1 and then n plus 1 and -1 and n. So what do we actually get when we could combine those? We have the same base. What can I do with the... We would have -1 to the 2n plus 1 over n. So now really think about what's happening on that numerator. If you want to, think about some values, plug in some values. What is really happening in the numerator?
It's just going to cycle between
Is it always? Check some values. What is actually happening there?
I don't know if that was going to be
Yeah, it's always going to be -1. So you would get -1 over n. So these really should all be equal to that one at the top because we just simplified. So what test can we say? What happens with this? We have left with -1 over n. Converge, diverge, how do you know what test?
diverges because P-series.
Yep. Diverges because of P-series. Now again, this is just for the 3, x equals 3 endpoint. So we know that 3 right now, for our final answer, 3 has to have a parenthesis because it diverged at that point. If it converged, you have the bracket. So now we have to test at n equals 7, or x equals 7. Now I'm going to erase so I have more room. Does everybody have the test for x equals 3 down? Okay. So let's test the other endpoint. So we want to test 7 now. That's what we're testing. So take the original, -1, okay. So this is the original, plugged in 7, so we have +2 now. So do we have to do any work, or can we cancel right away? Yeah, cancel right away. That leaves us with -1 to the n plus 1 over n. And what do we notice about this one?
This one looks like
Okay, this one on the numerator cycles between -1 and 1. It goes back and forth. That's known as what kind of problem? It's an alternating series. So this one we can't use P-series. We have to actually use our alternating series from that previous section. So What do we need to know about alternating series? If you need to look back, go ahead, but try to remember. What do we need to know about the alternating series to determine if it converges or diverges?
Take out the alternator. Kind of like, you like made it two separate things. And then, like that part, like, isn't wrong.
If you need to look back, go ahead and look back.
If you like take out the alternator and then test the limits, it goes to one thing.
Okay, so what should the limit go to?
The limit goes to
Oh, the limit.
What should it be equal?
Zero.
Okay, the limit should equal 0, so that's one thing. So if you think about the limit of 1 over n, or because you take the absolute value, does that go towards 0?
yes.
Yes. There's one other stipulation. The limit has to go to 0. And what about each term? Yeah, each term that comes after the previous term has to decrease. So as you go on in the series, do the terms get smaller? Do they decrease? Yes, and the limit going to infinity does go to 0, so this converges. By alternating series test. So that's why you're going to have to know those tests, and that's how this is building upon that. If you have to test your endpoints, sometimes it may not just be a p-series. You may have to use some other tests. So now we know our final answer has to have a bracket on these 7. Oh, there we go. So we have found radius of convergence when we're representing some function, again, with these infinite series. And we found the interval. If it's not all real numbers, we found the interval for which it is exactly the same. So for the case of this one, this is representing something. Again, we don't know what it's representing, but on this interval from 3 to 7, it's representing it exactly to the same value. Outside of that interval, it wouldn't be the same. So I was going to do the next example today too, but we will move on to that tomorrow. Okay, we'll stop right here for today.